Okay, this is another project support video. Some of you want to investigate climate change impacts, and if you want to work with climate data, you don't actually have to make up that data. You can get real data for current climate conditions, past climate conditions, and future projections. And I'll show you briefly how to get this for locations that you pick as study sites in the landscape. And so this will be useful for your course projects, but you can also use this approach that I show you here to design real studies where you first want to explore what maybe latitudinal climate gradients there are or elevational climate gradients you may find. And from there you can fine-tune your study designs. So let's say we would like to sample some lakes along a latitudinal gradient and maybe also pick some mountain locations here where we sample elevational transects to see how possibly how species communities change along elevational transects. So this will be a function of temperature as it gets colder, as you go up toward the tree line. And from those relationships, so plant-climate relationships or perhaps fish communities along temperature gradients, we can then also draw inferences on how those communities might be affected by climate change. So the first step would be to decide on your sampling sites, and you can get those coordinates or those lat long locations. So you can just zoom in if you want to, for example, place a sample at Lac La Biche. You can actually zoom into exactly where you want to take your sample, let's say right here, and you just right click and say what's here, and it will give you the exact coordinates of that location. So if you click on it, it will just show up here in that box, and we can copy it here and paste it on an Excel sheet. And so you get your latitude and longitude, and those are in decimal degree formats. So you can copy those over here. I have already done this. Usually if you just copy 3 digits in here, that's good enough. So that's one easy way to get your coordinates. Now these numbers here, they are given in decimal degrees, and that's good. That's usually what you also can get out of a GPS or how most geographical information systems process spatial information in latitude, longitude format. So it basically means the 54 and 112, these are actually degrees, but then the minutes and seconds have already been converted to a decimal that count up here to 99 and 100, and at 100 you would have the next, you would have the degree change to 113 degree. But sometimes you're also given coordinates in the standard degree, minute, second format. And so if you want to convert those, so if let's pretend for the mountain ecosystems we have been given preferred study locations in those decimal degrees. So I also want to quickly show you how to convert from degree, minute, second format to decimal degrees. So these are here my latitudes and those are my longitudes. And so in order to convert those, we need a little bit of space. I'm going to move those over here, and we have to copy this degree here, and then I can say text to columns, delimited is good, and our separator is the degree. So let's do this, and then we have to do this again. And this time our separator is the minutes. And we can just get rid of our seconds here. And now we have our latitudes and our longitudes in degrees, minutes, and seconds separated. So to get our decimal degrees, I take the degrees, add the minutes divided by 60, and add the seconds divided by 60 times 60 is 3,600, and that's my value. So I can drag this down. If you're not given the seconds, you can just skip the last step or leave it blank. It doesn't matter, the formula works anyways. And then here we have to add the minus, so that is sometimes forgotten. And we can do the rest here. And there are my latitudes and longitudes in decimal degrees. So we can just move this over here and save this as a CSV so that we get rid of all the formulas. And we just close it and reopen it. And there we are. So now we can get rid of all this. And we have our latitudes and longitudes in decimal degrees. Okay, so let's place our transects at those locations for my transect 1, transect 2, and transect 3. We can now get rid of the space here. And if I place transects, they will not be exactly at the same locations, all points, obviously. So if you were to go out in the field, those would be at slightly different locations. So for the purpose of the exercise here, we can just randomly vary this by small amounts. Let's say a quarter degree. So I'm going to say this is this value plus a random value between 0 and 1 divided by 4. And I'm going to do this for all my locations here. And I'm also going to fix the 7, C7 here. I'm going to put a dollar here, a dollar there for the 12th row, and a dollar here. And then I can fill this out. So that would be my complete data table for climate data extraction. So I already prepared that data table in the format that the climate extraction software wants it. So you start with 2 IDs, you enter your lat and long and decimal degrees, and you can put an elevation there. You don't have to. So you can leave this field blank if you don't know it, or if you have a preset value that you want to sample or that you recorded with a GPS, then you can put that there, and then the climate value will be estimated for this particular elevation. Okay, let's save this. And we're done here. So the next step would be to download the climate software. This is, you can get this if you're on the course website. You can just go to the data section, and there's for various parts of the world you can download climate data. There's also shortcuts, so the dataset for Western North America that I'm going to use here, that's tinyurl.com climate WNA for Western North America. So let's follow that link, and so the database behind it is a high-resolution database of all kinds of different climate variables, precipitation, temperature, snowfall, climate moisture deficits, and so on and so forth. And there are gridded data sets available for download here for current and future periods, but if you work with sample sites or particular locations, I would recommend you just download the software here. So save this, and so that comes down as a zip file. You just extract the files, and then in here you find the databases here in the folders and the executables. So let's copy our coordinate file into the folder, and we can run this, and you can pick an input file. So our coordinates, we specify an output file. So in this case, we're just starting with the 1961 to 1990 climate average. That's a fairly good baseline period, largely prior anthropogenic warming. So we're going to use the default here and say calculate, and there's our file. So if we open this, so what happened now is, in addition to what we entered here, it gives us all the climate variables for those particular locations and elevations that we specified. So you can see here in the far north, mean annual temperature is lower than in the south, and the same for the transects here. So we start at 4 degrees at 700 meters, and at 2300 it would be -1 for this particular location. So all the climate variable names that are used here, you can look up what they mean in the help file here. So if you scroll down, these are all the explanations for the climate variables that are available through that software. Good. And now let's also calculate data for a future period. So there are all kinds of different scenarios from modeling groups around the world, but we could just pick an ensemble mean, let's say for the 2080s. So that's the average of all those scenarios. We pick the input file again, that's again our coordinates. And the output file now gets a different name, default name. So you can just accept that, so we always know what it is. And hit calculate, and it's done. So those are the predictions for those locations for the 2080s. And if we flip between the two periods, so our past period, it goes from -3 to 5, and in the future, this is predicted to go from 3 to 10. And so those are real. This is real data. There's also historical data in here, so you could look at trends that have already happened with decadal data. So you can look at different decades or annual periods from 1901 to 2013. So all this is available. Okay, and lastly, I want to explain to you how to simulate biological response data to environmental gradients, such as a climate gradient. And we can work with that data table that we generated in the last video. You recall we had 2 different ecological site types, and then we had continuous predictor variables, mean annual temperature, with a range of temperatures from, I don't know, around 6 to 14 degrees. And we wanted to know how that affects height of a species. So we set this overall expectation to 15 meters. We set our ecological site type 1 has a more positive and the other one a more negative effect. And then we simulated a linear relationship. So the warmer it gets, the better the tree growth. But that's not necessarily realistic. So most of the time, there is an optimum for the species, and after a certain peak it declines. So I just want to show you quickly how to simulate something that's slightly more realistic. So let's say our range that the species can withstand goes from 0 to 20 degrees, and at 10 degrees it grows best. So let's say this is a +5. That's 5 meters above the average of 15, and at the ends here, that's the limit, so they're going to be dead. So let's call this -15 and -15. So if we look at this in a scatter plot, this can be approximated with a polynomial equation. So let's just add a trend line here. Polynomial second degree sounds good, and we want to know the equation. So that's our equation here, and let's put this in instead of the linear equation here. So we simply say, what is this, minus 0.2 times MAT squared plus 4x, so 4 times MAT minus 15, and expand this to the end, and now we have this sort of curvilinear relationship. So let's save this, and we can bring it into R as a CSV. So we're going to read this CSV that we modified. We'll do the same thing just like we did before. So we add some noise. We can look at our header. So I didn't clean this up, but it will still work. Attach it, and then plot it. And there we go. So now instead of having these two linear relationships, we have curvilinear relationships. And there is some noise, but this is how real world response functions actually look like. So they will be noisy because there's also site differences. It's not just climate that influences growth. So now you can use these functions, so we learn later how to fit them, but you can predict climate impacts on growth, for example, based on a data set like this.